not going to start magnets today. We'll use today as like our review for circuits, as if we were going to have a test soon, but we still have to do the magnets topic. The magnets topic goes kind of quick. You're going to want some time to study it because it's a little confusing, but there's not a ton of like lessons to teach you. So even though we still have a full topic left to do, the test isn't too far away, probably like 2 weeks or so, something like that. So definitely lock down your circuits, and then starting Wednesday we'll start doing magnets. So that should put us online to have a test sometime, middle of November or something like that. 2 weeks, 3 weeks. I'll give a quick overview of the topic we're in right now. Basically just all the formulas. Guys just through the topic, and then I have some review sheets, some multiple choice tests. But I think this topic is going to be more or most clear. So it's pretty obvious which way to go. We started the topic with current, which is I, but we measure it in A's, amps. And we said current was Q over T. It's the amount of charge that passes per second. So it's similar to a speed. It's the speed of electrons. Don't forget, we know how to calculate Q. It's the number of electrons times the charge of an electron. That E value was 1.6 times 10 to the negative 19. So current. Then we went to resistance, which is the opposite of current. If current's the flow of electrons, resistance resists electrons. It slows them down. That is measured in ohms. It is the resistivity, rho. That is a constant for each material. So you'll have to be given that times the length over the cross-sectional area. And then we brought, basically all this gets brought together, V equals I times R.
What's rho here?
Rho is the resistivity. It goes with the material.
No, it's given.
It's given. Yeah, sometimes there's a table, sometimes it's given to you. So like metals would have a low resistivity. Insulators have a high resistivity. So this brings everything together. I guess it should, the Ohm's law is more I equals V over R. If you increase the voltage, you increase the current. If you increase the resistance, you decrease the current. But I think this way is a safer way to write it. Ohm's law. And then from there we had our rules for series and parallel. We have series circuits and parallel circuits. Series is one after another after another. You can trace your finger in one complete loop. That would be, so if I want the resistance, the total resistance in series, it is R1 plus R2 plus dot, dot, dot. So you add them up in series. In parallel, it had this weird formula. 1 over R total equals 1 over R1 plus 1 over R2 dot, dot, dot. So a little more work to solve for resistance in parallel. Keep in mind, when you add a resistor in series, your resistance goes up. It's like going through more than one cashier over and over. That would slow you down. In parallel, if I add another resistor, it's like another lane opened up it actually increases the total flow. In a series circuit, the voltage is shared. The total voltage is shared between each resistor. And remember that voltage is a voltage drop. It's a change in voltage. It's what the beginning voltage and the end voltage is. So in series, it was add them up. Wait, yes. Add them up. V1 plus V2 plus whatever. That will give you the total voltage. In parallel, each one gets the same voltage. So they're just equal to each other. They're all the same. Your individual voltages is equal to the total voltages. And then for current, in series circuit, the current's the same everywhere. Oops, equal signs. No matter where you are in that circuit, there's just one current. In parallel, oh no.
It's like the abyss. I wonder how many things are down there.
There's a lot.
That's a poor design. Why would you go that way?
The box should open up too. Actually, does it?
In parallel, the current splits. There's different branches. So the individual branches, when they come back together, they should add up to the total. These formulas are not written nicely on your reference table, so you're gonna have to lock these to memory, or just, kind of, basically memory. They are on the reference table, they're not written in the nicest way. So this is basically the whole topic. It looks like 5 part 2 questions right there, right? Basically one of everything. Current, resistance. These might end up more like a multiple choice question because there's not much work to do here. It's kind of just a calculator problem. If it was a part 2 question, I'd probably ask you, what if I double the length? What if I triple the area or something like that along those lines? V equals IR goes into every question. And remember, you can do V total, I total, R total, or you could do like V1, I1, R1. So when you're going around a circuit and solving for everything, you might have to use that twice. And these, obviously, part two, solve, a whole circuit, find all the information. So, let's give this a look, practice some of these, make sure we know what we're doing, reviews everything we have. Number 1, we have to find the total resistance or equivalent resistance. This one. 1A, what type of circuit is that? Series or parallel? Parallel, right? There's no way to draw a complete path that goes through every resistor. So in that one, we would have to use this formula. 1/5 plus 1/7 plus 1/2. Those numbers? Yes. Will give me 1/R total. What's the common denominator of 5, 7, and 2?
40.
Not 35.
40. Oh no, it's 40. Never mind, 42.
This is some people forever.
40.
60. 70. Oh my God.
70?
70.
70.
It doesn't have to be the least common, right? It's just a common denominator.
70.
So yeah.
Right to it.
Nothing with 5.
14.
Or just works with 2.
14/70 plus 10/70 plus 35/70. I believe that would be where your work's at.
Yeah.
This is not a very convenient one.
Ugly.
Yeah. So what do we have? 24, 59 over 70. But remember, that's not your answer.
Right.
That's 1 over your answer. We want our total. So don't forget that final step. You can just flip both of them and we can say our total is equal to 70 over 59. So that would be the trickiest formula on this. What is 70 over 59 equals exactly?
The calculator says 70 over 59.
Beautiful. Decimal. 1.19. That's good. Because realize, so this is equal to, let's say 1.2 ohms. That is smaller than the smallest resistor. Our resistance went down. There was a 2 ohm resistor plus the other ones. Now we have even smaller than that. It's different. All right, the next 2 circuits are series circuits. So you can just add them up. B would be 7 ohms. C would be 14 ohms. Series circuit, much easier. Let's solve these 2 V equals IR charts. What do they give us? They gave us all 3 resistors. Makes it easier when they start this way. And they give us the total voltage in the battery. 6 volts. So you search around a little bit, you check your formulas. This is a series circuit, 1 loop. So first thing I would do is find our total. Add them up. We have 60 ohms is the total resistance. From there, I have a V total and an R total. I can find I total. .1 amps. 6 divided by 6. Where would you go next? What would we fill in next? Well, the current's the same. The current's the same everywhere, so we could write 0.1 in everywhere. And then we could do I times R in each individual one to find V1, V2, V3. So we have 1 amp, 2 amps, 3 amps, and that checks out. What's up?
Volts.
Am I doing them wrong?
No, the math is good. But
Oh, A's and B's. And that checks out because my individual voltages should add up to the total. So by the end of it, everything agreed with each other, and that would be that. Series circuit, I'd say, is much easier. Let's try the parallel one. Can I erase this?
No, leave it the same.
No way. Oh,
they were the same.
all the ones I erased. Oh. always save one. I don't know. 10 ohms, 20 ohms, 30 ohms. So, this way we could do 1 over 10 plus 1 over 20 plus 1 over 30.
Or you could avoid that and just do the
We could.
I V equals IR.
Yep. What would we have to do first? If I wanted to avoid using our total and using our tricky formula, what would we have to fill in first? All the voltages. Each resistor is going to go from 6 volts to 0 at the same time. So if you know one of the voltages, you know all the voltages. And why that helps us, we could find I1, I2, I3 by doing V divided by R. We would have 0.6 volts. That's 0.3. What's 6 divided by 20?
0.3.
Exactly?
Yeah.
Doesn't sound right.
Yeah, it is. But that's amps.
Oh no.
You're supposed to keep giving me fractions. Like give me decimals.
What's this one? 0.15?
1.
0.3 and 0.2.
0.2. And what that helps us do now is the total current should be the sum of these 3 currents. Put these together, it would give us our total current. So that would be 1.1 amps. So we didn't have to use the resistance formula now if we don't want to. We can do 6 divided by 1.1 to get our total resistance. We're expecting a number smaller than 10. What's 6 divided by 1.1? Somewhere around there. And I'm sure that would check out if we did it the other way. All right, let's try the next one because now this has been straightforward. They've given you the resistors. It's easier to start that way. Let's start in the middle of the problem where they give you mixed information. You have to hunt around a little bit. So let's draw this circuit. They give us the power source, 120 volts. And we have 2 resistors. R1 is 50 ohms. Oh, they give us an ammeter too. We don't have this second resistor. That's all we have. So part A, find the equivalent resistance. Find the total resistance. Well, naturally, you should look at the resistors and say, well, it's a series circuit, I should add them up. But I don't have the second resistor, so I can't do that. So my other option is V total, well, V equals I times R. We have to find some, it could be 1s, 2s, it could be totals. This is the current in one spot, but because it's series, that's the same everywhere. So this is my current, this is very useful. So I'm going to call this my total current, and I'm going to use my total voltage to get the total resistance. 120 volts, 0.5 amps, times R. our total will be 240 ohms. What'd you say?
Go with 60.
You're gonna have to divide by half. 120 divided by half, I think we'll get 240. So that's a different way to find the total resistance. And now they want the resistance just in R2. Well, the two of these should add up to 240. If you want the formula, R total equals R1 plus R2, which would be 240 ohms equals 50 ohms plus R2. So R2 is 190 ohms. So that was a little, closer to the level we're looking for. You gotta mix it up a little bit, show some knowledge. Similar deal, we'll try to parallel. This one I believe will be trickier. This is a parallel circuit. We have the total voltage. We have this ammeter, which is 5 amps. And we have this resistor. That's all we have. This current over here in A2, this is outside the branches. The current is coming around, well, it'll probably be coming this way. It's going to split right here, two ways. But then it comes back together right here. So this will read our total current. This, or if one was over here, that would read I1 or I2. That would be the current just in one of the branches. They split here, they come back together here. So this is our total current. So part A, if we want total resistance, we have total voltage and total current. $12 volts equals 5 amps times our total. 12 volts divided by 5. What does that equal? 2.4 ohms. Seven current just in this branch. What can we do? How would you find that?
Wait, how can it be a total of 2.4 if it shows one of the resistors is 3?
Because when you add a resistor, so if you just had this one resistor, the resistance would be 3, right? There's just one resistor. When you add another grocery line, everything moves faster. Current goes up, resistance actually goes down. So the total should be smaller than both of them, which is not natural. It doesn't, I added resistance, how does it go down? What do you think? How can we find A1? How can I find A1, which would really be I1? I want the current in just that branch. What do you see?
12 over 3.
12 over 3. You're doing our total voltage divided by R1. Why does that work out?
Because 12 volts equivalent to both of them.
Good. If our total voltage is 12, our individual voltages are 12. Each one of these resistors is going to go from 12 volts to 0 volts. 12 volts coming around, they drop across the resistors. So since we have the total voltage, we actually had the individual voltages as well. So we could do V1, I1, R1, 12 volts gives us the current times 3. So I1 in this case would equal 4 amps. Final step. Question? No? Final step, they want us to find R2. I have V2.
Isn't I2 1?
Correct. I'm going to need the current going through here. Well, here's our total current. Some of it is in this branch, 4 amps. So I2 must equal 1 amp. I1 plus I2 should equal my total.
Or total, we have total resistance, or 1 over the total resistance equals
That would be a pain to
1
solve.
over R1 plus.
You don't want to do that.
And now you're like.
It wouldn't be too bad. You could do that. I mean, you could do 1 over.
2.4.
Oh no. 1 over R2 plus 1 over 3. You could work on solving that if you are so inclined. Not recommended. I would do V2, I2, R2, 12 volts equals 1 amp times R2. Wait, yes.
We decided A, or whatever, current number 2 is 1 because it's just 4 plus 1 equals 5.
Yes, they should add up. So you didn't have to find every piece of information in this problem.
What if, like, since they didn't draw an ammeter in there, does it mean that it doesn't exist? Or we can assume
There's just
that
not a
it
device
exists,
there to show us, because if there was an ammeter, we could just look.
but there would still
There's
be
still
a
current, yeah.
reading, which we can say this is what the current reading is.
Yes.
Okay.
So in today's lab, we have to be very careful not to short out any of the boxes. One class shorted out 5 out of 6. Another class only 1 out of 6. So we're shooting somewhere between 1 and 5. hopefully. How do we short things out is if you ever connect both sides of the battery without a resistor. So if I take a voltmeter and put it like this, the current is just going to zip around here and that would short it. What? This is a voltmeter.
Voltmeter, a very high resistance.
This one will be safe. It's got its own.
Ammeter will show it
So we have to be careful how we set these up. The ammeter goes in the circuit. You're going to have clips. It physically is in the loop. The current runs through the ammeter. So yes, if you connected the other end of this ammeter over here, you could see the circuit you just made without a resistor. That would be the one that's going to burn it out. Voltmeter, you want to be on either side. You want to read the voltage before and the voltage after. So if you're ever getting something like 0 volts, you're probably setting that up incorrectly. So we're going to have to be very careful. If you got any electricians in your group, be before you power something, just check the circuit, just trace it with your finger, make sure it doesn't shut down. All right, so there's a few more questions on there. I could also give you this. This is just a standard multiple choice test. You'll see the questions can't get far from here. All right, say that every time. So they don't stray far from there. And then you do that. Not too bad. Sometimes I get
Except
creative.
for the basketball players, or the guy that grabbed the basketball.
Get right there.
One more.
So you could start like studying this material. I feel like we're pretty comfortable with this. Just stay fresh with it because we're gonna do magnets next and then have one combined test. All right, you want to take these with you and get over to lab early? We have to go to our friend, get equipment.
Now, before I go to the lab, because I registered this morning at 9 so it was at 8, 9 a.m. I got up. And
Fast, I don't think so.
they kept 2 classes were like,
Guy to know, do it.
and then there was one
Yeah.
lab